Hello, everyone. I am sorry that I have to be gone today, but I'm at a meeting, and so we're going to continue onwards just to stay on track. In the prior lesson, we completed section 3.3, which was on using division to find all of the x-intercepts of a polynomial so you could graph it. There were only 3 questions for homework in that section. I'm going to read them off right now. In 3.3, the 2 questions that were in the book were just practice with division, finding what the result is when you divide one polynomial by another. In question 3, you should have got x squared plus 3x plus 1. In question 5, you should have got 2x squared plus 3x plus 5. Then there was one question where I asked you to use division to find all of the x-intercepts and graph the polynomial. You should have obtained the following graph. You should have had an x-intercept at -1, one at +1, one at 2. They all have multiplicity of 1, which means they all go straight through those points. And you should have had a y-intercept of +2. The last part is your leading term should have been at odd power. It would have been a power 3, a cubic, and it would have been positive. So it goes down on the bottom left and up in the top right. So the graph sketch would have looked something like that. We do not know how low this point goes. That was the key, kind of the key idea from section 3.3. In this next section, we build on that, and then we're just kind of pulling the training wheels off, kind of doing a problem like that from the start. You'll see what that means here in a second. So to begin, you need your note packet out, and I'd like you to consider the first question that's at the top of the notes for section 3.4. You'll look, and I actually put this in the note packet. I ask you, what do you notice here? This is the process that we completed in the last lesson. This is called long division. Just like you did long division of numbers in elementary school, you do long division of equations, or what we call polynomials, in high school. So compare this process with this kind of shorthand notation over here and see if you can figure out how the two are actually the exact same. One's just a shorthand, though. So take maybe 30, 45 seconds, pause the video now, see if you can pick out what's going on for yourself, and then unpause it, and I will talk us through what this notation is over here on the right. So pause the video now, please. Okay, so what you might have noticed is, first off, so there's a 3 that goes in this box, and the reason why is because that's actually the x-intercept. If your divisor is x minus 3, the value of x that would make that be 0 would be 3. So 3 would be an x-intercept, so that's where this part comes from. You'll notice here that this is a 1, a 4, a -5, and a 5, and those are the numbers right here. And then you'll notice here's the 3. Well, let's use a different color, maybe blue. Here's a 3, here's a 21, here's a 48, and those are the numbers that result in the process of doing the division. Last part is, what about the 1, 7, 16, 53? Well, here's your 16s, here's your 7s, there's your 53. So it's actually your result when you do this. So there's the 7, 16, 53. The 1 would be right there. So it's a shorthand notation for this long division process. We call this process synthetic division. I'm actually not certain where the name comes from. But synthetic division is a technique used to divide polynomials. So you don't have to carry along all the notation of long division. But all it is, it's a shorthand way of writing out long division. It only works when you have divisors of the form x minus c. If you had a power more than 1 that you were trying to divide by, then you can't use synthetic. But we only usually care about ones when we're dividing by a power of 1 because those are x-intercepts. So that's why this has kind of been invented. So it's the exact same process as doing long division. It's just an organizational technique. If you look in the book, they will talk through the process for you in this section. It looks just like this. I am going to just work an example, though, because it's one of those situations where you could read about it, or it's much easier just to see an example. But if you look in your book, you'll see one just like this if you'd like to read it for yourself, if you think that would be helpful. But we're going to work one just all together. So the first thing that you note is you need to write the x-intercept in that first little box. So if they had the statement that x plus 2 is a factor, that means that x equals -2 is your x-intercept, and that's the value that actually would need to go into the box. So that's the first thing that they write. They say, you know, if you're dividing by x minus c in the long division technique, then positive 3 would be your x-intercept, so that's the value that you write in the box. The thing that you need to write across the top in your first row are the coefficients from your actual polynomial. So here, our coefficients are a 1. It's actually 1x cubed plus 0x squared minus 7x minus 6. So across the top, we're going to write a 1, a 0, a negative 7, and a negative 6. And then we're going to just draw a line where we're going to write all of our results. So following the same steps that they are saying here. After you write your coefficients down, the very first thing you do is you bring down the first coefficient. So in this case, you're going to bring down a 1. And then what you do is you multiply. You take your x-intercept value and you multiply it by the value that came down here. So negative 2 times 1 is negative 2. Okay. Then what you're actually going to be doing is you're going to be adding all of these values. Then it just goes. So 0 plus negative 2 is going to be negative 2. Then you take negative 2 times negative 2, and you'd get 4. Negative 7 plus 4 would leave you with negative 3. Negative 2 times negative 3 would be negative 6, and then positive 6. Let's just go in there. Negative times negative is positive, and if you add these together, you get 0, and this last part is your remainder. These then are the coefficients of the result. So it has to be, well, if we divided by x and my original was a cubic, my result must be a highest power of squared. So this would actually be my squareds, this would be my x's, and this would be my numbers, my ones, if you will, and this would be the remainder. So it means when I take x cubed plus 0x minus 7x minus 6 and divided by x plus 2, I get the following. I get 1x squared minus 2x's and minus 3. Which means if I took that and multiplied it by the x plus 2, I would get the actual original, which was x cubed minus 7x minus 6. The question asked us, though, to find all of the x-intercepts for this graph. Well, I still could factor this original. So I need two numbers that multiply to be negative 3 and add up to be negative 2. Well, that obviously is going to be x minus 3 and x plus 1, because it's negative 3 and positive 1. And now you would have found all of the factors for that graph, which means all of the x-intercepts can be obtained. X equals 3, which we knew about from the beginning. X equals negative 1. Sorry, the x equals negative 2 is the one we knew about from the beginning. And now we have all three. Why do we have three of them? Because the highest power is a cubic. So there you go. That's how you can use synthetic division if you'd like. You don't have to use synthetic. If you feel like you're good enough with long division, you can always just use long division too. I'm not going to force you to use one over the other, but some people really like synthetic, so there is the technique. Okay, now that we have that, we can kind of get to the heart of what this lesson is really about. So here's the idea. We're kind of just been building up towards really this topic. So all along there's been some hand holding that's occurred, if you haven't noticed. That is, one of the x-intercepts was always given to you, like it just happened a second ago. I needed to tell you that one of the x-intercepts was negative 2 in order for you to be able to do the division. So question is, how do I do this if I don't even know what one of the x-intercepts, is? Like, for example, in the last lesson that we did, I asked you to sketch the graph for this polynomial, and again, I gave you one of the x-intercepts. I said x equals 3. That's what allowed you to do long division and then find the result. So question is, how do we even know that x equals 3 was an x-intercept in the first place? Where do we start if we don't even have a single x-intercept from the get-go? So to answer that question, I'd like you to follow the following setup, kind of from the back to the front. So here would be an example of a polynomial, and our question is, how do we figure out, how do I find the x-intercepts? How do I figure out where the roots of the polynomial are going to be? Well, let's work it backwards. What if I gave you the original answers and asked you to kind of reconstruct what the polynomial must have been. So for example, what if I told you one of the x-intercepts was 3 over 2, or 1.5. The other x-intercept is negative 1/3. Well, if I solve this fraction, I could undo the 3 divided by 2. I'd multiply the 2 up here, and I'd end up with 2x minus 3. Same thing could happen here. I could undo the divide by 3, and I just multiply the 3 up. So I'd have 3x equals negative 1. Well, this must have been one of the parts that equaled 0. So in order for 2x equals 3 to be 0, I would need to subtract the 3 over the other side. So I'd have 2x minus 3 equals 0. Same thing would go on here. If I'm trying to find x-intercepts, I need one part equal to 0. Add the 1 over, I must have had 3x plus 1 equals 0. So that means I was always asking, when is 2x minus 3 equals 0, and when is 3x plus 1 equals 0, which really means that 2x minus 3 and 3x plus 1, those must have been the factors. And then once I had the factors, how do you get to the original? Well, you FOIL it, or you double distribution it back to the original function. So that's how we could unfold it. Now let's look at this though. I'm going to kind of erase the colors. Okay, here's the original equation. Check this. Negative 3 is my constant term. If you look at the constant term is formed from the factors of the top part of your answer. So what's 3 times negative 1? Well, that's negative 3. That had to form the numerator of your roots. If you look at the front part, this being a 6 here, why was this a 6? Well, it was a 6 because your denominators of your roots were 2 and 3, because those are the parts that you'd end up dividing by, because they're the parts that be out front. So this 2 and this 3, when you solve for it, those would get divided down, and this negative 3 and that 1, those are the top parts of the roots, the numerators of the roots. Those are what form the last parts of your polynomial. Those are the parts that would have to stay up top. So the takeaway message is, notice that the numerators are the factors of the 3, the negative 3 if you will, and the denominators are the factors of the leading coefficient. So when you find your roots, it turns out this is always true. The numerators are the factors of the constant term, and the denominators are the factors of the leading coefficient. That's what allows me to narrow my search down when trying to find the original first root of any polynomial. And we call this the rational zero or the rational root theorem. It says, instead of me searching forever and ever and ever for the very first root, I can narrow my search down. The possible ones that must exist, they must have the following property. They must have the property that they can be written as a fraction, where the numerator are factors of the constant term and the denominator are factors of the leading coefficient. Just as a little aside, in the story of the history of math, this is the best we have. There's actually no better technique that you learn if you learn higher mathematics. As prior stories concerning Tartaglia and Cardano that we read about, which involved the quadratic formula for third degrees, and then the eventual discovery by a French mathematician named Galois that there's no such thing as like a quadratic formula for degrees 5 or higher. This is our best tool. It is actually the fact that factoring numbers and polynomials is so difficult that allows us for internet and credit card security in the form of cryptography. So cryptography, codes for the internet security and credit card security, is actually based on the fact that it is difficult to factor. We have no better possible tool for polynomials than this. So an example of using that to our advantage. So let's say I had the following polynomial and I wanted to eventually graph it. Well, in order to graph it, I need to find one x-intercept or root or zero, whatever you want to call them, in order to find the rest. So the question is, how do I even find the first one? Well, we know I could search forever. I could try dividing by 1. I could try dividing by 2, and then 3, and then 4, and then 5, and then hopefully I eventually find one. Well, instead of just checking aimlessly, I can narrow my search down. I know the ones that must exist must have the property that the numerator must be a factor of the constant term, and the denominator must be a factor of the leading coefficient. So let's write those down to start. So the constant term is negative 2, or 2. I mean, negative 2 and 2 are going to have the same factors. And then the leading coefficient is a 15. So now I know that the possible zeros that I need to check are all of the numbers who can be written as a fraction, where its numerator are factors of the constant term, which is -2, and the denominator are factors of the leading coefficient 15, which means my fractions must be of the following form. So what are numbers that are factors of 2? Or essentially, what numbers go into 2? Well, 1 and 2 are the only numbers. And they could be positive or negative. What are the numbers that go into 15? Well, 1 and 15 and 3 and 5. And they could be positive or negative. And now I list out all of the possible combinations. So all the possible combinations would be, I could choose, maybe to start with 1 as my numerator, and then I'd have 1 over 1 and 1 over 3 and 1 over 5 and 1 over 15. Or I could start with 2 as my numerator, and I'd have 2 over 1 and 2 over 3 and 2 over 5 and 2 over 15. And then they could all be positive or minus. So instead of searching infinite numbers, I've now narrowed my list down to 1, 2, 3, 4, 5, 6, 7, 8 times 2. I've narrowed my list down from infinite numbers to check down to 16 numbers to check, and that's narrowed my search down a lot. So I know it has to, the roots have to be one of these 16 to start. Some of them might be more than one of the 16. So when they ask you to just simply list all the possible rational roots or the rational zeros, this is all they mean right here. So that would be the answer. Now we're going to work one from the very beginning all the way to the end. Let's say my goal would be to eventually graph this function right here. And I want to use the rational root theorem to find the very first one. Once I found the first one, then I could do kind of a synthetic or long division to find the rest. Or maybe if it's just a power of 2, I could just do regular factoring with it. So here we go. I know that instead of checking all of them, they must be of the form where the numerator is a factor of the constant term, which is -6, and the denominator must be a factor of the leading coefficient, which is a 1, which means my roots must be of the form where the numerator is either a 1, a 2, a 3, or a 6, positive or negative, and the denominator is a 1. Well, the nice part about dividing by 1 is really I just need to care about the top parts, because if you divide by 1, you just get the original result back. So it must be a positive or a -1, a positive or -2, a positive or -3, or a positive or -6. So instead of checking infinite numbers, I've now narrowed my list down to 8, right? So now we go testing. So maybe I test 1 first. If I test 1 first, I would do synthetic division. So put 1 in there, do synthetic division, bring down the 1. Then 1 times 1 is 1, and I'm adding. 2 plus 1 is 3. Then I multiply the 1 times the 3 and get 3. Then -5 plus 3 is -2. -2 times the 1 is -2, and then if I add -6, -2, I get a remainder of -8. Since the remainder is not 0, it means x minus 1 is not a factor. So x equals 1 is not an x-intercept. So I need to check the next one. Maybe I check 2 next. There's no specific order. You could check -1 next and be just as valid. We don't know, because like I said, there's no better process than this. So maybe we check 2 next. I'm going to use synthetic just to save a little bit of space. If you want to use long division, then go ahead and feel free. So 1, 2, -5, and -6 are the coefficients of my original polynomial. Now I do synthetic division. Bring down the 1. Then the 2 and the 1 will multiply to be 2. I am adding. 2 times 2 will make 4. 2 times 4 gives me 8. -5 plus 8 is 3. And then 2 times 3 is 6. -6 plus 6 is 0. And because that's a remainder of 0, I now know that x minus 2 is a factor. And not only is it a factor, I get the result. So that means for the original, x cubed plus 2x squared minus 5x minus 6, I know it equals x minus 2. And now these are the coefficients of the result. I have a 1x squared, a positive 4x, and a positive 3. And I can find the rest because this is a power of 2, and I can just do regular factoring. What two numbers multiply to be 3 and add up to be 4? Well, that's going to be x plus 1 and x plus 3. And now I've found all of the factors, and all of the x-intercepts would be positive 2, -1, and -3. And you'd be done. And you could graph it. So that's the power of the rational root or the rational zero theorem. I'm going to give you a chance to try. So pull out your whiteboard. I'd like you just to list all of the possible rational zeros. So this is like the first one we did with the rational zero theorem, just to state all possible zeros, just like the first example we did with the rational zero theorem. So pause the video now for maybe a minute and a half, unpause it after a minute and a half, and everyone's had a chance to try. Okay, welcome back. Here's the answers you should have got. The factors of the constant term at the end. The constant term is a 7 or a -7. And then the leading coefficient is a 1. So constant term, its factors are +-1, +-7. Factors of the leading coefficient are +-1. So that means instead of checking infinite values for using synthetic or long division, you only need to check 4. It means your x-intercepts are either going to be a 1, a -1, a 7, or a -7. Those are all of the possible ones. So technically there's 3 of them. So 3 of them are, all of them are listed in here. So one of these will not work and 3 of them will work. So that's a lot less numbers to check than all of the numbers. We're now going to work the process backwards. So the last part of the lesson is, what if I tell you what the roots are and then ask you to actually construct the original equation? Or maybe if I gave you a picture in the second example, could you construct the original equation that would go with that picture? One note I want to make is if the book lists a complex root, it means that it has a pair. And its pair is its conjugate. Recall that the conjugate for a complex root is if I gave you something like x plus 2y, then its conjugate would be x minus 2y, and that's actually what happens in this one. So, example, find a third degree polynomial that has roots or x-intercepts equal to 4 and 2y with a point that f of -1 equals -50. So here's what I know. I know the equation is equal to, it has a root of 4, which means it must have a factor of x minus 4. It has a root of 2i, so x minus 2i. But if you look right now, I only have 2 x's, and I said it's a third degree polynomial. That's why we call this the imaginary, the complex root must have a buddy, and its pair would be x plus 2i. Now I have x, x, x. I have a third degree polynomial. If I simplify this out and multiply the complex ones, it'll clean up a little bit. So if I actually multiply these ones out by distributing, I'd end up getting x times x would be x squared. Okay. X times x would be x squared. X times the 2i would be plus 2i. Negative 2i times x would be minus 2ix. And then negative 2i times plus 2i would be minus 4i squared. I'd then get x minus 4. In here, these middle parts would cancel out, so I'd get x squared and then minus 4 times I squared. Recall I squared equals -1, so this is -4 times -1, so that'll be plus 4. So my polynomial must be something of this form. I have x minus 4 times x squared plus 4. Look, it's a power of 2 and a power of 1. Together, that would make a power of 3. It needs to have the property, though, that f of -1 equals -50. So that means if I put -1 in for x, I need to get 50 back. So let's look and see if that's true right now. Well, -1 times -4, that's going to give me -5. -1 squared is 1, plus 4 is 5. So right now we'd have -5 times 5. That'd be -25. And that doesn't give me -50. The reason why is because there's a scaling factor out front. So all along, there could have been a number out front. I didn't know what it was. And so I need to adjust for the fact that this number depends on the point that I need to go through. So I said when I put -1 in, I need to get -50 out. So that allows me to figure out then what a would need to be. I already said this is going to be negative 5 times 5, which is negative 25. And now I know that a must need to be 2 if you divide by negative 25. So that means the equation that fits all of the statements would be 2 times parenthesis x minus 4 times parenthesis x squared plus 4. There's one in the homework just like that, so use this example to guide you with the one in the homework. We're going to work one more, and this is similar to one that I would ask on an assessment because it's a key idea. So the last one for today would be, what if I give you a picture of a polynomial and ask you to make the equation? So that's the backward of what we've done all along. All along I've been giving you the equation and asking you to sketch the graph. So here we go. Let's list what these zeros or the x-intercepts are. So if I look, I see there are 1, 2, 3 of them. There is one at x equals negative 2. There is one at x equals 1. There is one at x equals 3. Now I need to list their multiplicity. Well, I can see at negative 2 it bounces, which means around there it acts like a quadratic, so it must be a power of 2 there. Around the 1, it goes flat and then through. That means it looks like a cubic around that, so this would be a multiplicity of 3. And then around the 3, it goes straight through. That means it's going to act like a line, so a power of 1. If you look at all the multiplicities added up, 2 plus 3 plus 1 makes the 6. That's why it's a degree of 6. Now I'm going to use that to list what the actual factor must be. So I need it to be an x-intercept at negative 2 with multiplicity of 2, so that means this has to be x plus 2 in order to have an x-intercept at negative 2, and it has a power of 2, so squared. This one needs an x-intercept at positive 1, so it must be x minus 1, and it's a power of 3, so looks like that. And then last part is I need an x-intercept at 3, so it must be x minus 3. It's to a power of 1, so I don't write anything. If you want to, you could list a power of 1, but it's unnecessary. Now I know my equation looks like something of f of x equals, I don't know what that scaling factor out front is, a. I'm going to figure that out by this given point right here, the y-intercept. F of x equals a, and then there's an x plus 2 squared, an x minus 1 cubed, and an x minus 3. That will guarantee all of the x-intercepts. So I've guaranteed all of the green points. Now I need to guarantee that purple circled point. So I'm going to use the fact that 0 is my x value and my output y is going to be 12, which means if I put 0 in for x, I need my output to be 12. So I would get 12 equals a. 0 plus 2 squared, 0 minus 1 cubed, 0 minus 3. Then I just solve for a. 12 equals a times, what is that, 2 squared is going to be 4. Negative 1 cubed is negative 1, and I get negative 3. So 4 times negative 1 times negative 3, that's going to equal 12. So I divide by 12, and a then must be 1. So I would write the function as the following. You might see it just written as this too. If there's just a 1, you technically don't need to write it. You could just do x plus 2 squared, x minus 1 cubed, and x minus 3 without needing to write the 1. Either one of those is fine, but you needed to verify the fact that a was actually equal to 1 based on the value of the point that was given that was not an x-intercept. And that is it. It's a big topic, but it's kind of the heart of what we study at Algebra that prepares anybody interested in taking like a pre-calc class, depending on the major that you study in your post-secondary world. So that is it. Thank you very much. The answers to the homework are right here. If you'd like to leave the video paused while you work, that sounds good. Thank you very much. Have questions ready for me when I return, and have a good day.